Ultraviolet curing requires direct line of sight between the coating and the UV light source. This simple requirement frequently causes headaches for a process design team who need to cure complex 3D parts with recesses and curves. Even when parts have simple shapes, their sheer size can make curing them a challenge. Other factors such as productivity, process, and environmental conditions often present additional challenges. However, many of the UV process failures experienced during production are rarely the result of those challenges, but are due to three major reasons: a poor understanding of the interaction between the optical and physical characteristics of the coating formulation in the lamp system, an inadequate understanding of the UV curing process window, and a lack of process control and monitoring. The main goal of this tutorial is to provide a good understanding of the interaction between the end product, the formulation, and the light sources used in UV curing. This tutorial is divided into three major parts. First, an overview of the physical and optical component characteristics of the photochemistry and the lamp system. Second, an overview of the key steps within a generic UV process development. Third, the control method to maintain production stability. To begin, any UV curing process must be viewed as consisting of three major component parts, all integrally related. The end product determines the formulation components of the photochemistry. Target properties such as opacity or hiding, film thickness, hardness or flexibility, chemical resistance, resistance to abrasion or scratching, and adhesion are only a few of the properties that may represent the performance requirements of the end product. Production requirements, the physical shapes of the end product, the application methods such as the flow or spray coating, environmental regulations, and health and safety concerns are also defining aspects of the formulation development phase. The photochemistry is designed to achieve the target properties upon exposure to the appropriate UV energy. Formulation variables include a combination of monomers, oligomers, photoinitiators, and functional additives. The optical characteristics of the formulated material determine the most effective UV curing system to use. The UV curing system has a number of variables such as power, wavelength, and focus that will also have a significant effect on the target properties of the end product. The selection of these variables depends on the optical properties of the formulated material. Now, let's take a closer look at each step. Although we will be working with pre-formulated coatings, let's take a moment and quickly review the fundamental principles of UV chemistry. UV-EB chemistry cures by polymerization and cross-linking. There are a number of polymerization mechanisms. However, currently only two are used in UV curing, namely free radical polymerization and cationic polymerization. Both polymerization processes can be combined in a single coating formulation, which then are referred to as hybrid formulations. In either case, UV radiation energy breaks the photoinitiator molecules by either homolytic fission to create free radicals or heterolytic fission to create cations and anions. These free radicals or cations then combine with oligomers and monomers to form a polymer. Since the wide majority of coatings are based on free radical chemistry, let's concentrate our efforts within these formulations. Before continuing with the process development aspects, let's take a short review of the instruments used within radiation curing. Radiometry is used to measure most of the preceding characteristics and verify the process design. However, the most important principle of effective radiometry is that the measurements must be relevant to the process, or in other words, must be related to the development of the physical properties of the final product. By thoroughly understanding the lamp chemistry application interactions, more precise and useful specifications can be determined for what to measure in the design of a process and for the establishment of meaningful limits that can be applied to process monitoring. In addition, data from radiometers need to be communicated in a consistent and uniform way. This facilitates the duplication of the UV exposure conditions that produce the desired curing result. Attaining a specific set of physical properties in the cured film on an end product is ultimately what is important, and design information is critical to achieving an efficient process with an adequate operating range or window. Over the previous section of this video, we have reviewed various end product specifications, the coatings, formulation strategies to achieve these properties, available lamp systems, the physical and optical interaction between the formulation and the lamp system, and the use of radiometers to determine the process window. In the following section, we will follow through with individual process design functions affecting the application in a rather generic manner. The purpose for this approach is to eliminate the possible assumption that a given example is only useful to a given application. Process control is the effort to maintain the process within the defined process window established during the process development phase. As each variable has distinct effects on the overall system performance as well as on the final product, the purpose of quality control is to know when any individual parameter has changed before it threatens the overall process. Any process, irrelevant of its nature, is dependent on the stability of its operating parameters. With stability comes predictability. Only then can capability follow. In order to manufacture a quality product, the procedures used to determine the process are to be followed as closely as possible during production. The best time to establish the base process control data is when things are working at their best. Establishing and documenting process control data takes work and time. Consider it a solid foundation that will pay you back down the road. Process control allows the operating condition to be maintained at a desired trajectory by use of logic controllers and instrumentation. In order to find out the status of a process, sensors will be used to measure relevant process variables. The controller will decide what to do if the process is not in a desired state, and the actuator will execute the required action commanded by the controller.